Hi everyone, here we're going to go over the Atwoods machine lab. So, well, the theory for the Atwoods machine lab. So what the experiment, what the theory looks like is this, is that you have two pulleys and you have a string passing over both pulleys and you have two masses. So one of the masses, well first, if the masses are the same, then the whole thing is going to remain, the whole thing is going to be balanced, and because of that the whole thing will stay stationary. But what you're going to do is you're going to have different masses. So let's say that this one here is going to be, let's have this set up here. So here, let's say that you have this one is more massive, and because it's heavier, and this one, let's say this one is lighter, the heavier one is going to drop and the lighter one is going to rise. So from that we're going to give these two masses those specific names. So the mass that drops, I'm going to call it MD, or mass, or descending mass, and the one that rises, I'm going to call it MA, or M ascending mass. So that's the first thing, is that when you have these two masses tied to a string, the string is gonna, one of them is gonna drop and one of them is gonna rise. And the other thing is that because they're tied to a string, this object is gonna accelerate downwards with an acceleration a, and this one is gonna rise upwards with an acceleration a. But because they're both tied to the same string, they're both gonna have the same acceleration. So the purpose of today's lab is to verify an equation that finds the acceleration of those two masses. So the theoretical equation for the acceleration is going to be this one. So again, this is for the Atwoods machine. So the theoretical acceleration is going to equal gravity. Well, let's see why that is. The reason why these objects are falling and moving in the first place is because they're being affected by gravity. So there's going to be a gravitational term there. So the theoretical acceleration is going to equal the gravitational acceleration, but multiplied by a factor. And the factor is going to be the difference between the two masses, so the descending mass minus the ascending mass, and then divided by the descending mass plus the ascending mass. So for today's lab, you're going to be able to calculate the acceleration theoretically just by using this formula here. So this is just going to be a plug-in. All you need to know is the masses for each of the objects. So that's going to be the theoretical acceleration, but you're also going to calculate an experimental acceleration, and you're going to compare it to this one. So let's see how you're going to do that. So again, you're going to have the two pulleys, and you're going to have the strings, and you're going to have these two masses, and they're going to start off where one of them is down here at the bottom and one of them is here up top. And so this is going to be the ascending mass and this is going to be the descending mass, and they're both being acted upon by gravity. And now you're going to calculate the acceleration using another method, and what you're going to do is just to let it go. And you're gonna measure the distance that the descending mass drops. So since it's moving vertically, I'm gonna call that y, and let's just leave it like that. So we'll call that distance y. And you're also gonna measure the time that it takes for this object to drop. And from there, another equation for acceleration is gonna be this one. The acceleration is also given by, or in this case here, the experimental acceleration is also going to be given by 2 times the distance that the object moves, or in this case here, 2 times the height that the object drops, and divided by the time squared. So you're going to calculate the experimental acceleration by measuring the time that the objects drop. Well, so let's make a table here. So in the experiment, the computer simulation is going to automatically generate the data for you, but you'll get, once you run the experiment, you'll get a table, and a table is going to have the time that the object moves, the distance that the object travels, and you also will get the velocity, so I'll put that here also. But you'll be able, so from that, you're going to be able to calculate the acceleration using the following formula. And it's going to be so your experimental acceleration so the A experimental is just going to be 2 times the distance traveled divided by the time squared. So you're just going to be using these 2 columns here. So that's one way to get the acceleration by using the distance traveled and the time moved. So you're going to create a graph, or you're going to get the acceleration using these values, but next you're also going to get the acceleration by creating a graph. So let's see. So there's going to be another equation for acceleration. So this is equation 1. We just covered equation 2. And now again you're going to when you run your experiment, the computer is going to give you a table with 3 values. It's going to give you a table for time, distance traveled, and velocity. And here another equation for acceleration is going to be acceleration will be equal to velocity divided by time. And so here you're also going to get another way to calculate the acceleration. You're going to make a plot of velocity, the velocity data on the vertical axis, and a time data on the horizontal axis. And when you do that, you'll get a straight line. And in this case, the slope is going to equal also the acceleration. And I think I just call this a slope. So in today's lab, you're going to measure you're going to get the acceleration 3 different ways. You're going to calculate it theoretically for the atwoods machine just by using the masses. Then you're going to watch these 2 masses move by letting one drop and letting one rise. And from there, you'll get a table that has time and position. And using time and position, you'll calculate the acceleration using this formula, which is going to be 2 times the distance divided by the time squared, or 2 multiplied by the distance divided by the time squared. And we'll also get the acceleration from that same table, but now making a plot of velocity versus time. And there the acceleration is going to equal the slope. So that's the general theory for today's lab. The lab though is going to have 2 different parts. So in one case, you're going to calculate the acceleration where, let's see here, so let's go and do that here. So in part 1, you're going to have the pulley and the 2 masses. And in part 1, you're going to do these steps here. And the condition is going to be this, is that both masses are going to start off with the same value. And what you're going to do is that you're going to add 5 grams, or I believe it's 5 grams to one of them, and then run the experiment. And so you're going to get your data. You'll get your data for time, position, and velocity. So that, and then what you'll do is you're going to now increase both of the masses by the same value. So let's say you're going to increase this one by 10 grams, and you're going to increase this one by 10 grams. And then again, you're going to run the experiment and get your data for time, position, and velocity. And you're going to increase again by another 10 grams for both of them. So for part one, there is going to be a constant mass difference between the masses. So the descending mass is always going to be 5 grams heavier than the ascending mass. So that's going to be the setup for part one. Part two is going to be slightly different. So part two, you're going to have the pulley and the two masses. But for part two, the total mass is going to remain constant. And the way that you're going to do that and make this thing move is like this, is that you're going to have the two masses, the ascending mass and the descending mass. And what you're going to do is you're going to take away some mass from this one and transfer it onto this one here. And then you'll run the experiment. And again, you're going to get there's some mass added here. And then you're going to run the experiment, and then you'll get your table of time, position, and velocity. And again, you're going to take away some more mass from this one and add it on to this one. Or take away some mass from the ascending, so this is the ascending mass, and this is the descending mass. So you're going to take away some mass from the ascending mass and put it onto the descending mass. So that's going to be less, and now this one is going to be more, and you're going to run the experiment. So, and you're going to keep on doing that. So for part one of the experiment, you're going to get time, position, and velocity, but in each case, the descending, so this is the descending mass. The descending mass is always going to be 5 grams heavier than the ascending mass. And for part two, what you're going to do is you're going to transfer mass, you're going to remove mass from the descending object, and you're going to add that mass to the, let me repeat myself, you're going to remove mass from the ascending object, and you're going to add that mass to the descending object. And again, you're going to get the plots of time, position, and velocity. And in each case, again, what you'll do for all of them is to you'll be able to calculate a theoretical acceleration using this formula. You'll be able to calculate the experimental acceleration using this formula here, using the time, position, and velocity, time, position data. And you'll also get the acceleration by making a plot of velocity versus time. So that completes the explanation for today's atwoods lab. So now you can watch the actual instructions for today's lab.